We prove one of the fundamental theorems of algebra. It's not the fundamental theorem of algebra, but it's one of the fundamentals. Anyway, that's called division algorithm, and we prove the simplest version of that now. Okay, so theorem. It's called division algorithm. Let a and b be non-negative integers. And suppose b is non-zero. Then there exist possibly zero uh, there exist positive integers uh, integers q and r such that a is equal to b times q plus r, and r is between 0 and b. So greater than or equal to 0 and less than b. Okay, so that's the division algorithm. Now let's prove this theorem. Uh, so first case, if a is equal to b. In this case, we have a is equal to b times 1 plus 0. So this means if we set q equal to 1 and r equal to 0, then this condition is satisfied. So this is true. And second case, if b is greater than a, if a is less than b. In this case, we have a is equal to b times 0 plus a. So we could set q equal to 0 and r equal to a. And of course, since b is greater than a, this r is less than b, right? So again, this condition is satisfied. So this is true. Now, the case where a is greater than b, then what happens? For this case, we prove by mathematical induction. Okay. Now, suppose this claim is true for all uh, value of a. So suppose the theorem, maybe this is not appropriate. The claim is true. All a prime from 1 to up to a minus 1. So that means for every one, a prime that is either 1 or 2 or up to a minus 1, there exists some integers q and r satisfying this equation. So for any of these, we can find q and r appropriately. Now, since we're assuming a is greater than b, a minus b is less than a, and a minus b is greater than or equal to 1. Okay? So that means for this number, a minus b, we can apply the induction hypothesis. By the induction hypothesis, there exists let's say q prime and r such that a minus b is equal to b times q prime and r, where r is between 0 greater than or equal to 0 or n less than b. Okay. Now moving this negative b to the right hand side, we have a equals to b times q prime plus 1 plus r, and r is still the same. And of course q prime plus 1 is an integer, therefore the theorem holds. So we can put q equal to q prime plus 1 and r is just r. So therefore the theorem holds. And we are done. Oh, by the way, for the induction to work, we need to find the case for, we need to prove the case for a equal to 1. I forgot that one. But this case is actually included in the first two cases, in these cases. So if a is equal to 1, either this or this holds. So we have already proved the base case, so the induction holds, and the theorem is correct. Next, we want to extend this division theorem to include negative numbers. But before that, we need to define the absolute value or modulus. So here's the definition. For any real number x, so this may be an integer, we define the modulus of x or absolute value of x as this, which is this is equal to x if x is non-negative, and this is negative x if otherwise, that is when x is negative. Okay, so it's a very, very simple definition. So the absolute value or modulus of 7 is 7, and the absolute value of negative 7 is 7, right? According to this definition. So this inside is negative, so we apply this case. So negative of negative 7 is 7. And in this case, it's just positive number, so we apply the first case, and that is just 7. So because of this definition, the modulus of x is always non-negative. And you should also try to prove that the modulus of x is 0 if and only if x is equal to 0. Okay, so if this is true, then this is true. If this is true, then this is true. So you have to prove this one. And also, if the modulus of x is equal to the modulus of y, this means x is plus minus y, or y is plus minus x, same thing. So these are the basic properties of modulus or absolute values. Now let's introduce a more general version of the division algorithm. So that's a theorem. Okay, now in this case, a and b are any integers. and b is non-zero, then there exists some integers such that a is equal to b times q plus r, and r is greater than 0 and less than modulus of b. Okay, previously a and b are non-negative integers, but in this case they can be negative. Okay, let's prove this one. Uh, by the division algorithm, the first version, that is the one we have just proved before. We have the following result. So let's take the modulus of a and b, so that they are both non-negative integers. So this one is a non-negative integer and this one is a non-negative integer. So there exists q and r such that this equation is true and r is between 0 and modulus of b. Okay, so far so good. We just apply the previous version of the division algorithm. Now, we consider several cases. First, if r is 0, then we have, so if this r is 0, we have modulus of a is equal to modulus of b times q. So therefore, uh, uh, let's get rid of the moduli, and we have a is equal to plus minus b times q. To see this, first we take get rid of this modulus first. Then we have plus minus a modulus of b times q. Then get rid of this. So we might have positive b or negative b. So if we consider both cases, these signs may or may not be cancelled. So after all, we have this result. Okay. But anyway, from this we have b times plus minus q. Of course, positive or negative q, they are either way they are an integer. Therefore, the claim is true. And second case, if r is positive, that is, r is supposed to be non-negative, so these two cases are all there are. Okay. In this case, we consider several subcases. First, a. If a is non-negative, then we have, so we take the modulus of this part, we have a equals to modulus of b times q plus r. Okay, and now consider another case. If b is non-negative, then we have a, so get rid of this modulus. Since b is non-negative, we have just b. So the claim is true. And second case, if b is negative, then we have a is equal to negative b times q plus r, which is b times negative q plus r. So the claim is true. And next, so we covered all the cases where all the possibilities when a is non-negative. And then second case, when a is negative, then we have from this equation, then we have negative a is equal to modulus of b times q plus r. Okay. Then uh, moving this negative sign to the right hand side, we have a is equal to negative modulus of p times q minus r. Now, here is a problem. It's a negative number here. We want to make it positive so that this form of equation holds. R is supposed to be, this remainder part is supposed to be non-negative. So we want to make it non-negative somehow. And this can be done by adding and subtracting the modulus of p. So we add, maybe we should subtract here, and subtract modulus of p and add the same quantity. So we can factorize this part, and we have b and negative q minus 1 plus b modulus minus r. Okay. Now, if r is greater than 0 and less than modulus of b, this means this quantity, modulus of b minus r, is greater than 0. No, modulus of b minus r should be positive. And this quantity is, of course, less than modulus of b. So we have, after all, we have a equals to b modulus q prime plus r prime, where q prime is this one and r prime is this one. Okay. Now, let's see. So now we want to get rid of this modulus operation. So if b is non-negative, then we have a equals to b times q prime plus r prime, and the claim is true. And if b is negative, then a is equal to negative b q prime plus r prime, and b times negative q prime plus r prime. So the claim is true. So now we have covered all possibilities, and the proof is done. So according to this division algorithm, for any integers a and b, we can express them as like this. So there are always some integers q and r such that this holds. Okay, whether a and b are positive or negative. And this q is called a quotient. And this r we already used, it's called remainder.